Our next topic is to look into machinery faults that are associated with subsynchronous vibration. When we say subsynchronous vibrations, it is usually referred to the vibration energy that is below the fundamental frequency or below the 1 time RPM. So it could be the 0.4 time RPM, 0.5 time RPM, 0.8 time RPM, or any frequency components that appear in this particular region. The most common faults that are associated to subsynchronous vibration are oil whirl, oil whip, rotor rubbing, cage defect at the anti-friction bearing, and belt frequency related faults. Oil whirl is a machinery fault that usually happen at the sleeve bearings. It occurs when there is an excessive clearance between the shaft and the sleeve bearings. The excessive clearance could induce fluid instabilities on the lubricant oils and subsequently causing high vibration at the frequency components below 1 time RPM. Oil will usually show frequency component at 0.42 times to 0.48 times RPM. The dominant plane to detect this type of fault is the radial directions, either in horizontal or vertical directions. The phase angle in this case is constant. When transient analysis is performed or during run-up, oil whirl can be detected at the frequency of 0.42 to 0.48 times RPM over the increasing speed during run-up conditions. When the speed increases until it reaches the rotor's first critical speed, it will be locked at this frequency even after the 1 time RPM continue to increase and pass the critical speed. This phenomenon is named as oil whip. So the characteristics of oil whirl and oil whip is at subsynchronous components 0.42 to 0.48 times RPM for oil whirl and locked at the first critical speed for oil whip. Both can be detected from the radial directions, either in vertical or horizontal. For example, in a case study of a vertical pump, it was found that the 0.4 time RPM was so dominant in the spectrums, which was due to the pump multistage bush bearing wear. This subsequently has caused secondary damage to the flange, mechanical seals, and parted shaft. Our next fault that is usually associated with subsynchronous vibrations is rotor rubbing, in which the rotating parts are in contact with the stationary components. Rubbing generates truncated waveform which emulate the square wave and produce similar vibration signature to mechanical looseness. Rub can either be partial or throughout the whole revolutions. So in FFT, these patterns produce harmonics of the fundamental frequency of rubbing at 0.5 times RPM. We have previously discussed fault in the anti-friction bearing in the non-synchronous vibration topics. There are BPFO, ball pass outer race frequency, BPFI, ball pass inner race frequencies, BSF, ball spin frequency, FTF, fundamental train frequency. Please note that faults that are associated with the outer race, inner race, and ball are usually higher than 1 time and fall under non-synchronous vibration components. The defects happen at the bearing cage is usually associated to the subsynchronous vibration energies. If one wants to diagnose if any faults happen in the bearing cage, the FTF or fundamental train frequency of the bearing needs to be calculated in the first place. Any high vibration observed at that subsynchronous frequency components as calculated will then indicate these particular defects. Again, vibration technique like envelope analysis can be used to detect these faults. Lastly, for machinery which utilize belt pulley system, is usually exposed to another fault associated with the belting. It is related to belt pass frequency, BPF. The belt pass frequency can be determined by the following equations: pi times F times D over L, in which the D is the diameter of the pulley, L is the belt length, F is the rotational speed. When there is a fault associated with the belt, this frequency component or its harmonic will be visible in the spectrums. It happens that this belt frequency usually fall below the 1 time RPM of either the motor or driver or the driven machines. When there are cases like mismatch, worn, or loose belts, usually the 1 time of the belt pass frequency and its harmonics are visible in the spectrums, especially in the radial directions, either in vertical or horizontal directions, whereby the 2 time of the belt pass frequencies is usually the most dominant. The vibration amplitude in this case is usually fluctuating. For worn out belt, one can use stroboscope as a diagnostic tool. To check if the belt is worn out, usually for V belts, first shine the strobe at the belt frequency at the sheaths and check for shining groove bottoms. If the shiny groove bottom is observed, it means that a belt or the sheath is worn out and the belt is riding on the bottom instead of on the wall. By now, you should be able to identify and differentiate some of the machinery faults like oil whirl and oil whip, rotor rubbing, anti-friction bearing cage defect, and belting problem, which are usually associated to the subsynchronous vibration energy.